So I just want to look at a handful of things when it comes to extension 1 or the hard extension 1, because circle geometry, of course, is a particular favourite they have in extension 2, and that idea of using the converse of the theorem, showing something as a cyclic quadrilateral, and then once you know it's a cyclic quadrilateral, it opens up other theorems that you can use. So just as a reminder, this sort of situation, I mean, if you got a right angle triangle, well, obviously a circle goes round it, because I mean you can draw a circle around any triangle. But if it's right angled, then of course that makes AB the diameter of that circle because of angle in a semicircle. So we know, yes, they're concyclic, angle in a semicircle. The other one is that you see a lot, I suppose, when you're trying to prove something. This one's more useful because not only do you prove that the points are concyclic, because there's 4 points, you prove it's a cyclic quadrilateral. And that can open up other theorems, the opposite angles in a cyclic quad, things like that. So if you've got an interval, so AB, and you notice that there's 2 points where they've got the same angle, then effectively AB must be a chord, and they're subtending the same angle. So that gives us that AP, Q and B are concyclic. So it's our angles in the same segment theorem that we're using in reverse. I suppose if you actually have got a quadrilateral, I didn't draw a picture for that one. If you have got a quadrilateral and you notice the opposite angles are supplementary, that sort of idea. The 4 centres of a triangle. It may be useful, you may never use it, who knows, but these sorts of things. So the angle bisectors of the vertices are concurrent at what we call the in-centre. So there's a triangle. Oop, there we go. So the angle bisectors, they meet at the in-centre, and the circle you can create is the in-circle, because what you're basically saying is the vertices are all tangents from an external point, if you like. So it creates the tangents to the circle. So we call it the in-circle because the circle is inside the triangle. The circumcircle, so circum meaning around the triangle. So this is the one with the perpendicular bisectors. So if we want to find that, we get our perpendicular bisector of each side. It doesn't necessarily go through the vertex, of course, but they'll all meet at a common point known as the circumcentre, and from that point we can draw a circumcircle, because what we've got there is that the perpendicular from the centre bisects the chord. So that's the situation you've got in each case. Now, the centroid. The centroid. So let's draw that one up. That's the one with the medians. So the medians is where the vertex is joined up to the midpoint. They're also concurrent. The nice one about the centroid is it breaks the median up in the ratio 1 to 2. So it trisects it. So one part will be 2, one part will be 1. And the altitudes, so altitudes or perpendicular heights, they are also concurrent at what we call the orthocentre. Anyway, there's a lot of interaction between geometry and trig, so sometimes we can use trig to solve geometry problems. The most common one, I guess, is the sine rule. So you remember that we know the sine rule, A on sine A is B on sine B, C on sine C, but it's also equal to the diameter of, by the way, not if, the diameter of the circumcircle. So let's just prove that. So there's a triangle with its circumcircle. I'm going to draw in a diameter there and create another triangle. So angle A, of course, will equal angle P because there'll be angles in the same segment. So therefore the sine of A must equal the sine of P. Now PBC we know is 90 degrees, angle in the semicircle. So BC over PC must be the sine of P, looking at that right angle triangle. So BC over sine P is PC. But we said sine P was the same as sine A, so PC is equal to BC over sine A. If we go back and have a look at our actual triangle, and we'll see what we've got there. PC is the diameter of the circle. BC, I could call little a, as if we were using the sine rule. So there we have as A on sine A. Now, of course, I could have done that with any of the sides, so therefore it's equal to B on sine B is equal to C on sine C. By the way, those centres of the circle, an interesting fact about the circumcentre, the centroid, and the orthocentre, those 3 points will always be collinear. Right, so again, it might be a fact that we never end up using, but you never know. If it crops up, we can say, hang on, we know the circumcentre, the centroid, and the orthocentre, it's on what's called, he gets so much credit, this bloke. Does so much stuff, but it's his line apparently. So Euler's, however you say it, Euler's line is where those 3 points lie on. Okay, let's have a look at some examples. So 1990, whoa, that's a long time ago. So this is the diagram we were presented with. So AB is fixed, it's not moving. P, however, can move along the arc. And what else have they told us? AC and BD are perpendicular to BP and AP. So there it is, standard sort of question that we see so often in these extension 2 questions. Show something is a cyclic quadrilateral. So show ABCD is a cyclic quadrilateral. Now I like to sort of just draw in the quadrilateral they're talking about, and I get a different colour, and so then that way it sort of stands out and I can see it in more detail. But when you do, you'll notice, oh, hang on a sec, BDA and ACB are both 90 degrees. Well, there it is straight away, because that means we've got that situation of angles in the same segment. They're both coming from the arc, or the chord, whichever way you look at it, AB, but angles in the same segment we know are equal. So, okay, we've got that, it's a cyclic quad. AB, of course, must be the diameter, because not only are those angles in the same segment, but it would be a right angle, which makes an angle in a semicircle as well. The next part, show that triangle PCD and APB are similar. You'll notice I actually have now drawn in CD there, because I can use the fact that that is a cyclic quad. That might help me out in my proof. So PCD and APB are similar. Well, APB and DPC, it's the same angle. So that's the easy one to find there. Of course, with similar triangles, if I can find a second angle, that's going to be the quickest way of doing it. I can say PDC will equal PBA. Because now that I know that's a cyclic quad, PDC must be the exterior angle of the cyclic quad. Okay, so I know they're equal. Well, there's two angles. So, yep, they're similar due to equiangular or angle, however you want to write that one down. Okay, so the next bit, show that as P varies, so P, remember, is moving along the arc of the circle, the length of CD is going to be constant. So it doesn't matter where P is, it'll always have the same length. Okay. Well, there's PAB and PCD. They're the two triangles that we just proved were similar. I figure it's going to have something to do with that. Otherwise, why did they just ask me to prove they were similar? So I like to sort of draw them side by side so I get a feel for where the corresponding sides are and things like that. So I know then that CD over AB will be the same as PC over AP. Okay, ratio of sides in similar triangles. Now, if I look at triangle PCA, it's a right angle triangle. So PC over AP would be the cosine of P, cosine of angle P. So CD over AB must also equal the cosine of P, because we said those ratios were the same. So the length of CD will be AB times the cosine of P. We want to show that this is constant, but P is moving around our circle. Well, angle P will be constant, because whilst it's moving around the circle, remember AB was fixed. AB is not moving. So you're always going to have angles in the same segment, no matter where you put P. It'll be angles in the same segment. So the size of angle P will be constant. And AB, remember, was fixed. That's not changing. So in that case, CD must be constant. AB is not changing. Cosine of P is not changing. So CD is not changing. So okay, we now know CD has constant length. Does not matter where P moves along that major arc there. Find the locus of the midpoint of CD. All right, remember ABCD is a cyclic quad. We know AB is the diameter of that cyclic quad. Now M is the midpoint of CD. I'm going to call that. So what we're basically saying is, how's M moving in our picture? As we move P around the circle, M's going to move. What's it going to trace out as it moves? Well, O is the midpoint of AB, also the centre of that circle that goes around the cyclic quad. So therefore OM is going to be constant, because remember, we just proved CD was of constant length. So whilst the chord moves, its size is not moving. And we know equal chords are equidistant from the centre. So it does not matter where I place CD, OM will be the same length. So we're now saying, what's the locus of this point M, which moves, but its distance to the point O is always the same? That's got to be a circle. That's the definition of a circle. Point moves so that its distance from another point is always the same. So equal chords equidistant from the centre. So M is fixed. And, maybe I went a little bit crazy here. Yes, I could say it's a circle, but I'm going to actually find its radius. There we go, look. The length of OM. Well, OC is half of AB, and MC is half of AB cos P. Square them, I get a quarter AB squared sine squared P. So I know the radius is a half AB sine P. That might have been a bit of overkill for that question. But essentially we've got, yes, it is a circle, and I know its centre is O. And all right, the radius is a half AB sine P. Okay, let's do one a little bit more recent. 2008. Even that's 10 years ago now, but it's a nice question. So in our diagram here, we've got P, Q and R lying on a circle. Tangent at P and the secant QR, they intersect at T. Bisector of PQR meets QR at S, and those angles are equal, QPS and RPS. The intervals RS and SQ and PT, yet they've labelled them on the diagram for us as A, B and C. All right, so they've set up the actual problem. We need to show that angle TSP is the same as TPS. TSP, TPS. TSP, all right, well, let's have a look. RQP, well, that's our alternate segment theorem, isn't it? RQP is equal to RPT. Okay. Now, TSP is made up of RQP and SPQ. Okay. Oh, because of exterior angle of the triangle. Okay. So from that, I can say that TSP is equal to RPT, because we said that was equal to RQP, and SPQ, they've told us, is theta. Okay, let's keep going. SPT is all equal to RPT plus theta, common angle. So therefore, SPT and TSP are the same. All right. Hence show that 1 over A is equal to 1 over B plus 1 over C. What? How do we... It's got one of those feelings of one of those inequality questions here, but it's in circle geometry. What's going on? There's our diagram. It's going to come in handy. I know triangle TPS. If we look at that one, we now know it's isosceles, right, because it's got 2 equal sides. 2 equal sides. So that's TPS. So ST is also equal to C. Okay. Now I use the old endpoint of the chord to the point of intersection times endpoint of the chord to the intersection is equal to endpoint of the chord to the point of intersection times endpoint of the chord to the point of intersection. But it's a tangent situation here. So it's PT squared will end up being QT times RT. And so endpoint of the chord to the point of intersection times endpoint of the chord to the point of intersection is equal to endpoint of the chord to the point of intersection times endpoint of the chord to the point of intersection. So C squared, now remember we've said ST is equal to C. So QT would be C plus B and RT would be C minus A. So expanding that out, C squareds are going to cancel, and I've now got BC is equal to AC plus AB. If I divide everything by ABC, we get it. All right, look, the best sources now for questions are probably our past HSC papers and seeing the sort of circle geometry questions that they did ask. But there is, in the handouts there, Cambridge 10A has some, and of course in Patel